So good evening. I'm Nikos. I'm part of the LibreSpace Foundation, and today I'll talk about SatNOGS, one of our main projects, a crowdsourced satellite operations network. And starting off, just a few words about who we are and what we do. So, as I said, I'm a member of LibreSpace Foundation. LibreSpace Foundation is an organization we launched actually for backing up SatNOGS, and we started that about 4 years ago. So we're all in the foundation pretty much free software activists. We have the background of contributing to open source and free software communities for many years now, and we believe that the value of free software and open source should be applied to any field, and space included. So we try to push the boundaries of open source to the final frontier, to the space. So we started, as I said, 4 years ago from a local hackerspace in Athens, Greece. It's a hackerspace that, it's a physical space, so it works like any hackerspace. I guess you've been to a lot of them. So it's a physical space that gathers a diverse community with various skill sets. So we have people that are software developers, we have people that are radio amateurs, space enthusiasts, mechanical engineers, so on. So this physical space gave us the opportunity that it gathered in one place many people with different background and different skill set. And as you can see along the talk, SatNOGS is a project that actually utilized many different skill sets and many different kind of people. So back in 2014, a few months after we started the project, we won the Hackaday Prize, which was, as far as I remember, the first Hackaday Prize, the first Hackaday contest. So we won the prize for the SatNOGS, and that was a very significant moment for us because the prize was a big funding channel for us, so it helped us grow the project, but it also made the project very well known outside the boundaries of Greece. And although we started from our local hackerspace, today the project is global. We have contributors all over Europe, Australia, United States. You will see later on we have ground stations very much in many continents. So why did we did this project? So you know that out there are thousands of satellites. Most of them are nano satellites like this one here, and nobody's listening to them. Nobody's communicating with them. There are so many satellites and so many teams and hackerspaces and academia who build satellites, who launch them, who put them in orbit, but they don't actually talk to them. Especially in the nanosatellites category, we know that this is a huge area. We know that there are many satellites launched every year. Only in, if we see this graph, for instance, only in this year alone, around 400 to 400 new CubeSats have been announced that will be launched and put in orbit alone. So all of these teams put a lot of effort and a lot of money in some cases to build their satellites, to put them in orbit, and sometimes they don't put the same kind of effort and the same level of effort to build a ground station to communicate with the satellite or just listen to the satellite when it's up there. And that, of course, it's a task that it's not easy and it doesn't scale. I mean, imagine if 500 different teams around the world were building 500 different ground stations just for their own satellite, just to wait for that moment in the day that their satellite passes over the head, just to listen to it. So the idea we had back then was, what if we try to create a network? What if we try to apply the open source mindset to the ground station area? So build a decentralized, crowdsourced network of ground stations, and somehow these ground stations can managed globally and also be transmit back the data to a global management place. So for instance, if I am a satellite operator in Brussels, I can utilize a ground station in the other end of the world and listen to my satellite. So use a ground station that is not built by me, it's not owned by me. We'll dive more into the technical details of the project, but this is a high-level image of what network actually means. So we have the users, where the users could be, as I said, satellite operators, but they also could be pretty much anyone. It can be people who just like to listen to satellites, or radio amateurs, and so on. Using a global management network, they can utilize the ground stations that are scattered around the world, and these ground stations then observe, listen to the satellite, or communicate with the satellite and get the data back to the users. So in order to do that, we try to actually make the project as modular as possible. The idea was that many of the building blocks of the project maybe were already out there, so many people have already ground stations, but not in a network fashion. Or other people may have want to use their own Linux laptop or even use a gpredict or any other software to listen to satellites. So we try to build the project as modular as possible, so you don't have to use all the building blocks in order to participate in the network. We also try to use, not to reinvent the wheel, and use as many open source projects and libraries out there that make our life easier. And whenever there was something missing, we actually built it. So this is a graph that shows the building blocks of the entire project, and we'll dive more into the more big blocks of that diagram. So in a high level, this is the 5 most important building blocks of the project: the network, the client, the rotator, the antennas, and the DB. So starting from the rotator, you can see one right here. We try to not just to build everything open source and open hardware, but it was important for us to also be accessible and cheap to anyone. So all the parts of the rotator are things that you can either 3D print or you can easily buy very cheap in a store. And that's, at least for me personally, it's also one of the most important things about open source, that it actually removes barriers for people to participate. But as I said, the project is modular. So if you don't want to build your own ground station, if you already have a ground station, the project supports any rotator that is supported by Hamlib and a lot CTLD. As I said, we wanted to make the rotator and all the building blocks of the project accessible, so we try to keep the documentation as up-to-date as possible. And in the hardware side of things, we try to have documentation that guides you through the process of building a ground station step by step. We have our own Ojai instance. Ojai, for those of you who don't know it, it's a hardware documentation platform built by Latchbot. It's an open source web application where you can see step by step and with photos how to actually build all the parts that you see in the rotator here and assemble it to create a rotator. It's also important to emphasize that in order for a rotator to be accessible, it's not enough just to be open hardware, it's just enough to put the schematics out there. It was also important for us to try to use open source toolchain, so it's easy for people to contribute, but also to design their own modifications and so on. So we try to use open source tools in the entire process. And that can mean that can be CAD software to design, KiCad here, QCAD, and in the end to produce our own hardware in an open source, in a fully open source way. And also to be easy for people in hackerspaces and universities to follow the documentation through without any need to pay any license or any other cost. So the ground station is not just the rotator. The ground station also needs some kind of software to run on it in order to do the observations and return back the data and so on. Our reference platform is Raspberry Pi and an RTL SDR. But as I said, it's modular, so someone may use something completely different. You may use an Odroid, you may use a BeagleBone, or you may use a Linux laptop. And it works with any SDR that's supported by ZR Osmo SDR, and as I said, any Linux platform as long as we can run Python and GNU Radio on it. So you can see in the photo, for instance, a small box of a ground station with a Raspberry Pi and so on. It's really small and portable. And Raspberry Pi 3 being our reference platform, so what we provide is also, as I said, we use open source tools too. So we utilize the power of GitLab, the power of GitLab CI specifically, to actually, and Ansible, to actually provide, to do nightly builds of the software that runs in the ground station and to build ready images for the Raspberry Pi with everything prepared. And all you have to do then is just to run a small configuration script and the ground station is ready to go. So we have many variations of ground stations from contributors around the world. Not everyone follows the same design or doesn't necessarily follow our reference or our reference designs. These are all ground stations that are currently hooked in the network from United States, from Australia, from Denmark, Greece. And as you can see, for instance, down here, it's in Copenhagen. There's a ground station that doesn't have a rotator. That's a very simple setup with no rotator at all, just a specific antenna. And these ground stations are, as I said, all over the world. I'll get to the network side of things in a bit, but as you can see, we're very geographically spread. So going back to the, leaving for a moment of the ground level and going to the cloud, so to speak, side of things. This is the SatNOGS DB. This is probably the sub-project of SatNOGS that it has a usability that it's beyond SatNOGS itself. So when we started the project, we realized that there's no one central place to find information about satellites. Frequencies, for instance, the most important thing. And the only way to find info about satellites was actually to just browse blogs and radio amateur websites and try to figure out which transmitters have on each satellite. So what we did, as we did with the whole project, we launched a website that works in a crowdsourced way, where people submit suggestions about satellites they know about. They can be that they are the satellite operators, so they know what their satellite actually, what frequencies actually has, or other people that have that information. And we gather all this data in one place, so you can easily see you can easily see satellites, some basic information about them, and the frequencies they support, what's their status, and so on. In the process of building DB, we also expanded its scope and started to also make it usable to other cases. Well, first of all, let me say that DB has an API, so it's pretty much an open data portal, so everything that's on DB can be consumed by an API, and that was really important for us. But also the API is it's a doorstep for people who don't use our ground stations, who don't use our network, but are still doing observations for satellites, to somehow submit raw data of observations out to the world. So right now our API supports, besides our own software, it also supports third-party software like gPredict or TLM for water and so on. When I wrote the slides, we had about 10 million frames for 80 satellites, probably it's more now. And in general, we have about 300 satellites on these websites with detailed information. And what we do with with all this data. We try to, well, some satellites, we know for some satellites they have a specific specification of how they construct their binary data, so we write decoders for them. We try to decode the data and so to display the telemetry information about the satellites. We did that for our own satellite. We do that for other satellites depending on how much knowledge we have for a specific satellite. And from time to time we cooperate with satellite operators to give us that kind of information. And the idea here is that eventually we want to build some telemetry dashboards for this information so that it's easy for people, satellite operators or any other person out there to easily look at the data in a form that it's human readable, not just binary data, but actually readable data. So let's go to the network of SatNOGS. This is the main orchestration platform of the whole network. This is the place where you go if you want to make observations, to see the data that other people have gathered from observations and so on. So network has the primary functionality of scheduling observations, and that can happen in two ways. Well, first of all, the satellite operators themselves can go on the website and let's say they want to listen to their satellite for the next 5 hours, so they can see which ground stations are available in this time frame and schedule this observation in the future. But also for people who are just curious or they're radio amateurs or space enthusiasts, they can have their own ground station there and they can go on their own ground station and say, for instance, in the next 5 hours, which satellites I can hear, and then schedule these observations in the future. So when the observation happens in the end, in the ground station then posts that data back to the network, and you can actually see and hack with the data. So what is this data? As I say here, waterfall, the modulated audio and the modulated data. What this means, I have some screenshots so you have a more visual image of the network. So here, for instance, is the view where someone can schedule an observation. So here, for instance, we have picked NOAA 19, a weather satellite, and we can see that there are two ground stations that have an observation window free for this specific satellite, for this specific time frame, and for that specific frequency. And here is the other view I talked about. Here is a specific ground station, random example from SLAVBAT, where we can see what are the next passes, satellite passes above this specific ground station. And you can easily schedule observations. Also, you can see here that before you actually schedule an observation, you can see some metadata about it. So you actually know if that pass is a good pass or maybe it's too low and it doesn't work to schedule it, so on. And this is how the observation looks when it's actually done and the ground station has pushed the data back to the network. So this is the audio with a spectrogram, so you can have a more visual representation of the audio. And on the bottom you can see the TLE, the orbital data that was used for that specific observation. We try to keep TLE per observation, so historically you can easily know which TLE was used for any given observation. And on the left, you can see the same metadata we saw before. So you can see what time frame was, what was specific properties of this satellite pass. And on the left, we have a standard waterfall of the observation, so you can have a quick look on the observation. And on the right, this is a weather satellite, so weather satellites send back images, so photographs. So here we have the NOAA satellite posting back an image. So one of the challenges we had when the network grew, at the moment we have about 20 ground stations in production and fully functional around the world. and we have about 50 satellites that are in testing mode and about to get in production. So one of the challenges we have, besides scaling all this infrastructure, was also the challenge of storage. So the audio, for instance, is 50 to 60 megabytes per observation, and of course we want to keep all observations forever. That's the point. Even observations that are not perfect. So we had the challenge of where do we store all this data? And here we utilize the power of open data. As I said, all the data are in an open license and distributed freely. So what best to use already available public infrastructure for storing open data. So we wrote some code to actually utilize archive.org API, which is S3 compatible API, to upload that, at least for now, just the audio files of the observations to archive.org. At the moment, I think we have around 60K of audio data to archive.org, which is about 2 terabytes. So coming back to the ground station side of things, as I said, I show the physical side of the ground station, the rotator, like here, and the box with the Raspberry Pi and the SDR. But inside the Raspberry Pi, we have some software that does all the things necessary to do the actual observation. So what the client software does is it gives the necessary commands to the rotator, collects the future schedule of the observations from the network API, and adjusts the frequency for Doppler correction, and then when the observation ends, it generates the data, the waterfall, the audio, and pushes the data back to the network. So we have, as I said, we can easily client is part of the Raspberry Pi image, so you may not have to actually install it on its own as a standalone, but you can download it and install it on your laptop. And it also comes with a web interface, so it's easy to see some logs without having to SSH to the Raspberry Pi and to do some very basic configuration from there. So here is the web interface of the client, of the software that runs on the ground station. So imagine that you have a ground station like that on your rooftop. Then the only thing you have to do is power it up, do some very basic configuration, and then opening a localhost port on your laptop and see that web interface. You can see, for instance, here that that specific ground station has 4 scheduled observations in the future, and on the bottom you can see some real-time logs of what's happening in the Raspberry Pi. Also on the top right of the screen, you can see there's a drop-down menu for choosing between network mode and standalone mode. When it's network mode, it means that the ground station is part of the global network. But for many people, it's important to also have the ability to put their ground station in offline mode, in a standalone mode, so they can do observations without actually either pushing the data back to the network or even not pulling observations from that. And that's also a part of the sub-system of the web interface, where for our own satellite, we build our own web interface on the client for command and control. You can listen more about that in the next presentation. So how we can contribute to the project? As I said, it's a modular project, has many building blocks, and there are many different areas where people can contribute. We're in developers meetup, so you can write code for the project. The languages we use depend on the specific part of the project, so most parts of our software is usually Python, but we also have some bits of C and C++. You can contribute, of course, with other ways. We also are in need for mechanical engineers or electronic designers, and you can also help with automating things, testing, stuff like that. And we always want people to try, especially on the ground station level, to try with the Raspberry Pi, to flash it, to see problems, and get back to us. And of course, why not build a ground station on your own. It's not that difficult. I'm a software developer and I have my own ground station in my rooftop, so how hard can it be? So thank you.
Thank you very much. We've got plenty of time for question and answers now, so if you've got a question, just raise your hand and we will come to your place with a microphone. Up there, okay.
Hi, excellent presentation. Is there any IP associated with the data beamed by the satellites down to you, or are you free to redistribute it, as you said, with an open content license?
Can you speak a bit louder?
Yes. Is there any intellectual property, are there any intellectual property rights associated with the data by the satellite launchers? I understand that you make them freely available, but are there any rights associated with the data as they are beamed down from the satellite?
If I hear correctly, you're asking about the data of this?
Intellectual property rights of the data from the satellites.
From the satellites. Yeah, right now, as I said, we do it in an open data fashion, so all the data that are coming from the observations and are posted to the network are, we're using a Creative Commons license, so it's easy for people to actually manipulate the data and do whatever they want with that.
What about the generators of the data, so the satellite owners, launchers? Do they make their data available in that fashion?
The metadata of the SatNOGS DB, for instance.
No, the data of the satellites, the primary data generated by the satellites.
All the data that comes to us, at least, it's we redistributed in an open license. And I didn't mention that most of the satellites we're target are in the low Earth orbit, and most of them are using amateur bands. So the transmissions are open, and it's okay for everyone to listen, and that's why we also redistribute them in an open license.
Thank you.
Hello, thank you for the presentation. I wondered about the data that satellites are sending back again. You showed some of the binary data earlier and you showed some of the weather satellite pictures. How much of the data are you able to decode?
I'm sorry, I can't hear you at all.
How much of the data you get back from the satellites are you able to decode, or is much of it unknown?
How much of the data we get back of the satellite?
Yes. How can you decode the data? How much of it are you able to decode?
I can't hear you very well, but if I got the question right, how much of the data we get from the satellite we can decode, or?
Yes. Do you know what the data means, or?
Yeah, well, that depends. Yeah, that depends on how much information we have for the specific satellite. So in some cases it's really easy because it's well-known satellites, like I showed the example of a weather satellite. In some cases we know the satellite operators, or for instance for our own satellite, so we know the spec that this specific satellite is using, and we know how to decode this data. But that's an ongoing process. I mean, we try to have as close cooperation as possible with satellite operators, because it's not sure that all the satellites use similar kind of specs for their data.
My question would be, are there any regulated limitation in the frequencies? So can you collect the data everywhere on all the frequencies, or there are some limitations? And how do you implement those limitations?
So the data we collect are collected by ground stations, so the bands, the frequencies that you support is what the ground station supports. So depending on the antennas you have, you can hear the specific frequency. If you have a UHF antenna, you can use the UHF band and so on.
So it's allowed to collect data in those countries on those frequencies?
Yeah, I mean, it's a radio amateur frequency, so in most countries, at least in Europe, it's legal. So it depends on the country, but in general, yeah, if it's in amateur bands, it's legal. Thank you.
So are there any more questions? Ah, yeah. Sorry.
Okay. How do you interact with commercial stations from satellites? Is there a connection?
Commercial ground stations? You mean how, I mean, we don't have, so the ground stations that are, we don't offer a commercial package, if that's what you're asking. I mean, the network is, right now, anyone who has a ground station on the network can schedule an observation. That's the model we have right now, at least, to use it as an incentive for people to build ground stations. So in order to schedule ground station, in order to schedule observation, you don't have to pay, you don't have to rent a time slot on specific ground stations and so on, as it may happen in commercial examples. But yeah, the ground station, the observations are also public, so there's no commercial aspect of the network at this point, and we don't intend to.
You said earlier in your talk that people shoot satellites into space and then don't use them. Why the hell is that? What happens?
Can you repeat?
You said it early in the early parts of your talk that people shoot satellites into space,
Yeah.
but then don't use them, don't listen to them. Why
Yeah.
are people doing that?
Well, as I said, first of all, in the rush to try to build a satellite, sometimes you don't consider the ground station part very important, so you don't put much effort to that. And also, there are cases where even if you build the ground station, you just have to wait for your satellite to pass over your head, and that can be 1 or 2 per day, or if you're very unlucky, it may be never, because of the orbit. So sometimes it happens. I mean, there are so many satellites out there, and there are not so many ground stations.
Are there any more questions? Are there?
Yeah, I can see that you've got lots and lots of ground stations in Europe and maybe some in America. Are there any parts of the world where you specifically would like to have new ground stations because your coverage is patchy?
Yeah. Well, in general, the more the better. I mean, even in places where we already have a ground station, it's important to have more ground stations so we can catch as many satellites as possible. But if you look at the map I showed earlier, that's actually from the, I think that's from the, this also includes satellite, ground stations that are in testing mode, but you can see that we lack some ground stations, for instance, in Africa or near the equator and so on, and in North Asia, Russia, for instance. But we also, surprisingly, although you can see that Europe is full of ground stations, I think we don't have many ground stations in the Central Europe. We don't have in Germany or in France ground stations at the moment, or even in Belgium. So if you want to contribute in that way, that would be very helpful.
Are there any more questions? Just wave your hand then. Okay, doesn't seem so. So thank you very much for your talk.